Friends, today our lesson is waves. 11th chapter. What knowledge we are going to get. So in this unit, the students is exposed to waves and the types, transverse and longitudinal, basic terms like wavelength, frequency, time period, and amplitude of a wave, velocity of transverse waves and longitudinal waves, velocity of sound waves, and etc. we are going to see in this lesson. Introductions. In the previous chapter, we have discussed that oscillation of a particle. Consider a medium which consists of a collection of particles. If the disturbance is created at one end, it surely propagates and reaches the other end. So that is, the disturbance produced at the first Morse point is transmitted to the next neighboring Morse point, and so on. Notice that here only disturbance is transmitted, not the Morse points. Similarly, the speech we deliver is due to the vibration of our vocal cord inside the throat. This leads to the vibration of the surrounding air molecules, and hence the effect of speech information is transmitted from one point in the space to another point in space without the medium carrying the particles. Thus, the disturbance which carries energy and momentum from one point in space to another point in space without the transfer of the medium is known as waves. Standing near a beach, one can observe waves in the ocean reaching the seashore with a similar wave pattern. Hence, they are called ocean waves. A rubber band, when plucked, vibrates like a wave, which is an example of standing wave. These are shown in the diagram. Other examples of wave are light waves, that is electromagnetic waves, through which we see and enjoy the beauty of nature, and sound waves using which we hear and enjoy the pleasant melodious songs. Day-to-day applications of waves are numerous, such as mobile phone communication, laser surgery, and etc. Ripples wave and formation on water surface. Students, you can see the ripples formed due to disturbance of still wave by the particle. Suppose we drop a stone in a trough of still water, we can see the disturbance produced at the place where the stone strikes the water. So we find that this disturbance spread out, diverges out in the form of concentric circle of ever increasing radii, that is ripples, and strike the boundary of trough. This is because some of the kinetic energy of the stone is transmitted to the water molecules on the surface. Actually, the particles of the wave medium themselves do not move outward with the disturbance. This can be observed by keeping a paper strips on the water surface. The strips move up and down when the disturbance passes on the water surface. This shows that water molecules only undergo vibratory motion about their mean position. Formation of waves on string. Let us take a long string and tie one end of the string to the wall. If we give the quick jerk, a pump like pulse is produced in the string. So such a disturbance is sudden and it's lost for a short duration. Hence this is known as a wave pulse. If jerks are given continuously, then the waves produced are standing waves. Similar waves are produced by a plucked string in the guitar. Formation of waves in a tuning fork. When you strike a tuning fork on a rubber bat, the prongs of tuning fork vibrate about the mean positions. The prong vibrates about the mean position means moving outward and inward as indicated in the figure. When the prong moves outward, it pushes the layer of the air its neighboring, which means there is a more accumulation of air molecules in this region. Hence, the density and also the pressure increases. These regions are known as compressed regions or compressions. This compressed air layer moves forward and compresses the next neighboring layer in a similar manner. Thus, a wave of compression advances or passes through air. When the prong moves inwards, the particles of the medium are moved to the right. In this region, both density and the pressure are low. It is known as rarefaction or elongation. Students, you can see the vibration of tuning fork through this picture. Characteristics of wave motion. For propagation of waves, the medium must possess both inertia and elasticity, which decides the velocity of the wave in that medium. In a given medium, the velocity of wave is a constant, whereas the constant particle in that medium move with different velocities at different positions. Velocity is maximum at the mean position and zero at the extreme position. Wave undergo reflections, rarefactions, interference, diffraction and polarization. Mechanical wave motion and its types. Wave motion can be classified into two types. One is mechanical wave. Waves which require a medium for propagation are known as mechanical waves. Examples: sound waves, ripples formed on the surface of water, etc. Non-mechanical wave. Waves which do not require any medium for propagation are known as non-mechanical waves. Example: light waves, infrared rays, etc. Further, waves can also be classified into two types. One is transverse waves and another one is longitudinal waves. What is meant by transverse wave motion? So, students, you can see that a person swinging the wire stitched at other end, the particles are moving perpendicular to the motion of the wave in the string. We will see clearly now with the help of this clear explanation. Now see that in transverse wave motion, constituents of the medium oscillate or vibrate about the mean position in a direction perpendicular to the direction of propagation. That means direction of energy transfer. Longitudinal wave. In a longitudinal wave motion, the constituents of the medium oscillate or vibrate about their mean position in a direction parallel to the direction of propagation. That means direction of energy transfer. So which is shown in the diagram. Example: sound waves traveling in air. This diagram shows longitudinal waves formation. So compressed, stitched. This is the wave makes by the spring. Difference or comparison of transverse and longitudinal waves. Transverse waves. The direction of vibration of a particle of the medium is perpendicular to the direction of propagation of waves. Longitudinal waves. The direction of vibrations of particle of the medium is parallel to the direction of propagation of waves. The disturbances are in the form of crest and troughs. The disturbances are in the form of compression and rarefactions. Transverse waves are possible in elastic medium. Longitudinal are possible in all types of medium, solid, liquid and gas. Terms and definitions used in the wave motion. Suppose we have two waves, so those waves are identical. No tough. Now the two waves are both sinusoidal. There are many differences between them. Therefore, we have to define some basic terminologies to distinguish one wave from another. Consider a wave produced in a stitched string. See that wave is transverse waves. The crest and trough, that the wave above from the mean position called crest and below which is trough. If you are interested in counting the number of waves created, let us put a reference level mean position. Here mean position is a horizontal line shown. The highest point in the shaded portion is called crest with respect to the reference level. The lowest point on the unshaded portion is called trough. This wave contains repetition of section O to B, and hence we define the length of the smallest section without repetition as one wavelength. So the length OB or length BD is one wavelength. The Greek letter lambda is used to denote one wavelength. For transverse waves, the distance between the two neighboring crest or trough known as wavelength. For longitudinal waves, the distance between two neighboring compression or rarefaction is known as the wavelength. The SI unit of wavelength is meter. Velocity of waves in different media. Suppose a hammer is struck on a long rail at a distance, and when a person keeps his ear near the rail at the other end, he or she will hear the two sounds at a different instants. The sound that is heard through the rails, that means solid medium, is faster than the sound we hear through air. This implies that velocity of sound is different in different media. In this section, we will derive the velocity of waves in different cases. The velocity of transverse waves along the stitches string, the velocity of longitudinal waves in an elastic medium. First one is velocity of transverse waves in a stitched string. Let us compute the velocity of transverse traveling waves on a string. When a jerk is given at one end, that means left end of the rope, the wave pulse moves towards right end with a velocity v with respect to an observer who is at rest frame. Consider an elemental segment in the string. Let A and B be 2 points on string at an instant of time. Let DL and DM be the length and mass of the element string, respectively. By definition, linear mass density mu is equal to dm by dl. Dm is equal to mu into dl. The element string AB has a curvature which looks like an arc of a circle with the center at O, radius r, and the arc subtending at an angle theta, the origin O. The angle theta can be written in terms of arc length and radius as theta is equal to dl by r. The centripetal acceleration supplied by a tension in the string is centripetal acceleration is equal to v square by r. The centripetal force is FCP dm v square by r. From equation 11.6, dm v square by r is equal to mu v square dl by r. The tension T acts along the tangent of the element segment of string at A and B. Since the arc length is very small, the variation, students, you can see that vibrations or waves formed due to the stitched string. So, in the tension force can be ignored, we can resolve T into horizontal component T cos theta by 2 and vertical component T sin theta by 2. The horizontal components at A and B are equal in magnitude but opposite in direction. Therefore, they cancel each other. Since the element arc length AB is taken to be very small, the vertical components at the A and B appears to act vertical towards the center of the arc, and hence they add up. The net radial force F is F radial is equal to 2d sin theta by 2. Since the amplitude of the wave is very small when it is compared with the length of the string, sin theta by 2 nearly equal to d theta by 2, hence radial force Fr is equal to 2d into theta by 2. Simply we'll write t theta, but theta is equal to dl by r. We get Fr is equal to t dl by r. Applying Newton's second law to the elemental string in the radial direction, under the equilibrium, the radial component of the force is equal to the centripetal force. Hence, the derivative 11.9 and 11.12, we have T dl by r is equal to mu v square by dl by r. So, v is equal to root of T by mu. So, observation. The velocity of string directly proportional to the square root of the tension force, inversely proportional to the square root of linear mass density, and independent of the shape of the waves. Velocity of longitudinal waves in an elastic medium. Consider an elastic medium having a fixed mass contained in a long tube, that means cylinder, whose cross-sectional area is A and maintained under the pressure P. One can generate longitudinal waves in a fluid either by displacing the fluid using a piston or by keeping a vibrating tuning fork at one end of the tube. Let us assume that the direction of propagation of waves coincide with the axis of the cylinder. Let rho be the density of the fluid which is initially at rest. At t is equal to 0, the piston at left end of the tube is set into motion towards right with the speed u. Let u be the velocity of the piston and v be the velocity of elastic wave. In time interval delta t, the distance moved by the piston delta d is equal to u into delta t. Now, the distance moved by the elastic disturbance is delta x is equal to v into delta t. Let delta m be the mass of the air that has attained the velocity v in a time delta t. Therefore, delta m is equal to rho a delta x is equal to rho a v into delta t. Then the momentum impaired due to motion of the piston with the velocity u is delta p is equal to rho a into delta v and delta t into u. But change in momentum is impulse. The net impulse is I is equal to delta pa into delta t, or delta pa delta t is equal to rho a v into delta t into u. Now delta p is equal to rho vu. When the sound wave passes through air, a small volume element delta v of the air undergoes regular compression and rarefaction. So the change in pressure can also be written as delta P is equal to K into delta V by V, where V is the original volume and K is the bulk modulus of the elastic medium. But V is equal to A into delta X is equal to AV into delta T, and delta V is equal to A into delta D is equal to AU into delta T. Therefore, delta P is equal to K into delta U delta T by AV delta T is equal to K into U by V. Comparing the two derivatives, we'll get rho vu is equal to k into u by v, or v square is equal to k by rho. So velocity is equal to root of k by rho. In general, the velocity of the longitudinal wave in elastic medium is v is equal to root of e by rho, where e is the modulus elasticity of the medium. For a solid one-dimensional rod, v is equal to root of y by rho. Here y is the Young's modulus of the rod and rho is the density of the rod. Therefore, three-dimensional rod 3D is equal to the speed of longitudinal waves in a solid is v is equal to root of k plus 4 by 3 rho by rho, where rho is the modulus of rigidity, k is bulk modulus, and rho is the density of the rod. For liquids, v is equal to root of k by rho. Here k or b is called bulk modulus and rho is the density of rod.